Hello, I'm Will White, curriculum developer and instructor here at Solar Energy International, and I'll be your presenter for this lesson on battery technologies, where we're going to compare different battery types and different battery chemistries and look at the things we need to think about when deciding on which battery to choose for a specific project. There's a couple things we need to think about and keep in mind when we're comparing different battery technologies. And I just want to point out that this is a very brief overview. There's a lot more things and more nuances that go into comparing battery technologies. But these are going to be the main things that we need to think about. When we're looking at battery cost, there's a couple of different ways we can look at it. Upfront cost is an obvious one. How much is it going to cost us to purchase the batteries outright? And then we can also look at the cost over the lifespan of the battery. We typically do that by calculating how many kilowatt hours we will get out of the battery over the lifespan of the battery and dividing that by the cost of the battery to give us a cost per kilowatt hour. We could see very different numbers when we're comparing upfront cost versus lifetime cost. Very often, battery technologies that have a high upfront cost last a long time. Over the lifespan of the battery, have a lower lifetime cost. These are both things we need to think about when comparing batteries. We need to look at the longevity and the cycle life, which are basically the same thing. Cycle life is how long the battery is going to last, how many cycles or discharges and recharges we can get out of that battery. Different chemistries, different brands will have different cycle lives. We also need to think about maintenance. How much time am I or the customer going to need to spend keeping these batteries working? We have a picture of a flooded lead acid battery bank on the slide. Those batteries need to have distilled water added to the battery on a regular basis. There's time and expense involved in that maintenance. Other types of batteries, like lithium-ion batteries, don't need to have electrolyte added to the battery. There's relatively little maintenance other than the occasional visual inspection required for most lithium-ion batteries, so very little expense for maintenance in that battery type. Net efficiency is the comparison of how much energy or power I'm going to put into the battery and how much I'm going to get out. If a battery is more efficient, I'm going to have to put less energy into it to get the same amount of energy out, all things being equal. If the battery is less efficient, I'm going to need to put more energy in to get the same amount of energy out. We need to take that into consideration when designing our systems. Energy density may or may not be important to your application. This is comparing different battery chemistries on a capacity per weight or size basis. Typically, we're doing watt hours per kilogram. If a battery is energy dense, meaning it fits a lot of capacity into a small amount of space, then it's going to take up less space. It's going to be easier to transport. Energy density might not matter. If we're in a application where it is a fixed installation in a house, it's just going to be put into the house and left there, energy density might not matter. If we're in a place where we have to transport the battery long distances, maybe to a remote site, or we have a limited amount of space, then energy density may be something that you need to consider. The amount of power that a battery can produce is based on the internal resistance of the battery, and it's going to vary by chemistry. The lower the internal resistance, the higher amount of power that battery will be able to provide. The higher the resistance, the lower amount of power that battery will be able to provide. And it goes both ways. It counts for both charging and discharging. So power will impact how quickly I can recharge the battery and the size of the loads that I can power at one time. Batteries have different maximum depths of discharge. This is the amount of the capacity of the battery we can utilize. Depth of discharge directly affects the longevity of the battery. The more of the battery capacity that I am using, the shorter the lifespan of the battery will be. And the impact of that depth of discharge versus cycle life really depends on the battery chemistry. Lead acid batteries are more impacted by depth of discharge than other battery chemistries like lithium ion. Most lead acid batteries, we don't want to discharge them below about 70%. Even 50% might be the maximum depth of discharge for systems that are regularly cycling lead acid batteries like off-grid systems. Lithium ion batteries, we typically see anywhere between 80 to 100% recommended depth of discharge, and it has much smaller impact on the cycle life. When we're looking at different battery technologies, there's a couple of things that we need to keep in mind. Is this battery technology compatible with the balance of systems electronics equipment that I'm working with? Is my inverter or charge controller going to work with the configuration of this type of battery? Historically, lithium-ion batteries were relatively new. Not all equipment worked with them. That has changed pretty significantly, and most electronic equipment works with lithium-ion batteries these days. Almost everything works with lead acid batteries. They're so common that that's what most of the equipment was designed to work with. What's the temperature range of the battery? We need to look at the manufacturer's literature to determine that. Some batteries, like lithium-ion batteries, in many cases cannot be charged below freezing. Do you have an application where that might be a condition that the batteries are exposed to? That might not be the best choice of battery for that situation. Other batteries have different temperature requirements. They might have a maximum high temperature that they can tolerate. Those are all things we need to look at. We also want to look at the safety and toxicity of the batteries. Some batteries, especially lithium-ion batteries that contain cobalt, tend to be more volatile than other lithium-ion battery chemistries that don't contain cobalt. Cobalt's also a toxic chemical, so we need to think about that. Lead acid batteries contain both lead, which is hazardous, and acid, also hazardous. So we need to look at those and see, where are these batteries going to be located, what conditions are they going to be subject to, and how are we going to recycle them. Toxic stuff needs to be handled in a very specific way, especially when we get to recycling. Lead acid batteries have been around for a very long time. There are recycling facilities for lead acid batteries in most parts of the world. They're capturing more than 90% of that battery and recycling it. Lithium-ion batteries are much more challenging to recycle. There are very few lithium-ion battery recycling facilities around the world, although they are becoming more common as the technology is more widely adopted. The warranty is something that you're really going to need to read closely, especially with lithium-ion batteries. They may have very specific limitations in the warranty to how they can be installed, whether they need to be connected to the internet so they can report back to the manufacturer, whether they have specific temperature limitations. There's also going to be information in there about depth of discharge versus cycle life in many cases. So we need to very closely read that warranty and see what terms and conditions are there. We don't want to void that warranty. Let's look at some common battery types that we see used with renewable energy systems. Flooded lead acid batteries that we see here are one of the most common types of batteries, especially with off-grid systems. They're kind of the original battery that was used with battery-based systems. After that came valve-regulated lead acid. There's two types of those batteries, both gel and AGM, or absorbed glass mat. This is a sealed lead acid battery. There is no access to the electrolyte. They're called quote-unquote maintenance-free. There's no need to add distilled water to that electrolyte. They do not off-gas under normal situations. They can be mounted on their side in many cases to have different mounting options, unlike a flooded lead acid battery, which can't be tipped on its side because it would spill the acid out of the battery. There's two main types of lithium-ion batteries. Lithium iron phosphate, or LFP, is one. The other one is lithium nickel manganese cobalt, or NMC. Different manufacturers use different cells in their batteries. They could be either LFP or NMC. Each has their own characteristics. LFP has a little bit better longevity, where NMC batteries have a much higher energy density, so they take up less space for the same amount of capacity. Nickel iron is a type of battery that is less commonly seen. They are used most often in off-grid systems. They have a very low efficiency, but they are very robust. They're very hard to damage, and they last for a long time. They are a flooded battery. They are not an acid battery. The electrolyte in the battery is actually a base. So we do need to add a significant amount of distilled water to these batteries because they use a lot of water. So quite a bit more maintenance than other battery types, but they are quite robust. They can be highly discharged. Even if you fully discharge them and run the voltage way down, it has little impact on the longevity of the battery. They can also be operated at a partial state of charge, so they can float between, say, 50% and 70% state of charge without damage to the battery, unlike lead acid batteries, which need to be recharged on a regular basis. A couple of key points for this lesson. There are lots of things we need to consider when choosing a battery type. We have just scratched the surface. There's a whole bunch of other things that we need to look at when we're looking at picking a battery. There are a couple different battery chemistries that we see used with renewable energy systems. Lead acid batteries, both flooded and sealed. Lithium ion batteries, LFP and MC, a couple of different chemistries that are most commonly seen in renewable energy. And I should say that there are many other chemistries of lithium ion batteries, but they are less commonly used with renewable energy. And then nickel iron, which we see occasionally in off-grid systems. We very rarely, if ever, see nickel iron batteries used with grid-connected multi-mode battery-based systems. I hope you learned something about choosing a battery technology in this lesson, and I look forward to seeing you again. Thank you very much.